Welcome to this video on estimating a population mean. By the end of this video, you should be able to determine the critical value for a C% confidence interval for population mean, and you should be able to state and check the random, 10%, and normal or large sample conditions for constructing a confidence interval for a population mean. Alright, so today's scenario is, I wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. I selected a random sample of 30 cookies and found the weight of each cookie in grams. The mean weight was X bar equals 11.1921 grams with a standard deviation, or sample standard deviation of 0.0817 grams. We're going to make a 95% confidence interval to estimate the true mean weight of Oreos. So our point estimate for the true mean is our statistic, X bar equals 11.1921. If they give you that whole decimal like that, you should use that in all of your calculations. Don't shorten that up. Okay, so let's identify some important pieces of information. Our population here is going to be all Oreos. Our sample was the 30 Oreos that I selected. Our statistic was that point estimate, that's our sample mean. And then our parameter, we always need to define a parameter. Up until now we've been doing all proportions, but now we've gone into means, and so you need to use the parameter notation of mu, and mu represents the true mean weight of all Oreos. Okay. So what's the random sample? We're going to kind of go through this and remind you some important information. And if it was, why is being random important? Why do we care about that? So it does say this was a random sample of 30 cookies. So yes, it was random. And this is important so we can generalize to all Oreos. You want to be able to generalize to the population. In this case, the population is all Oreos. Okay. So what is the formula for calculating the standard deviation of a sampling distribution? So when we look at our formula sheet, okay, for the sampling distribution, so that's on the back. So sampling distribution for means, we only have one sample. And here's our standard deviation right there, okay? So we had the standard deviation for a sampling mean was the population standard deviation divided by the square root of n, okay? Now, what condition must be met so we can use this formula? This formula can only be used if you have independent sample, or you have sampling with replacement. Well, we never have sampling with replacement. So we have to have this 10% condition. There's a particular rule that if you follow your 10% condition, you can use this standard deviation because you're not changing the probabilities enough. The 10% condition, and it's met because 30 is less than or equal to 1/10 the population of all Oreos. Okay, so we're okay there. Oreos really would be an infinite population because they keep making more. Okay, so in the formula for our standard deviation of a sampling distribution of X bar, we actually don't know the value of sigma or our population standard deviation. Actually, if we did know that number, we would have known the population mean also. So that means we have to use the sample standard deviation. And that means we're calling it, we no longer call it just standard deviation, we call it the standard error. So even though they look, the formula is pretty much the same, we just want to use a different term. The standard error is, instead of the population standard deviation, because we don't have that, we're going to take the sample standard deviation and divide it by the square root of n. So you can see it's the same process, it's just where did that number come from. So in this case, our sample standard deviation was 0.0817, and we had a sample size of 30, so we're going to divide it by the square root of 30, and I got a standard error of 0.0149. So when we calculate that out. Now, would it be appropriate to use the normal distribution to model the sampling distribution of x bar? Justify our answer. It is appropriate, and here's why. In proportions, we use large counts, but there's actually 3 different things we can look at with our means, and one of them is the central limit theorem. We touched on that back in chapter 7. So you want to look at the sample size. We had a sample size of 30, and the number that you would compare that to is it has to be greater than or equal to, and it's actually 30 is the comparison number. So 30 is greater than or equal to 30. So we have a sufficiently large sample size, and that's called the central limit theorem. We could write CLT, but we have to state that this is allowed because of the central limit theorem. Okay, so that has to be part of our information. Okay, so before we go on to number 8, let's kind of go back and look at what we've got. So number 3, was this a random sample? It was, and that's our first condition that we should check. You have to have a random sample. Okay, and then we had our 10% condition. So just like before that we've been checking, we're going to continue to check our 10% condition when we're sampling without replacement. And then your third condition is a little bit different for means, but it's something that we have talked about before, and that is it needs to come from a normal population or have a sufficiently large sample. So either the population is normal or we have a large sample. In this case, we have a large sample because it didn't say anything about the population. All right, here's where it's a little bit different than proportions. We were using Table A, the z-score table, to find our area under the curve when we were working with proportions. But with means, we have a little bit of a problem going on because we're actually estimating 2 of the parameters. We're estimating not only the mean, we're also estimating the standard deviation. So you have a lot more variation going on with your statistics because you're using in for 2 numbers from a sample. So there's a little bit more error in there. So we're going to use something called T star. Okay, so it's like Z star, but it's a T. Okay, and so we were doing a z-score formula where we took the mean minus the parameter and we divided by the standard deviation. This is what we were doing before. But when we're doing a confidence interval and we're getting these numbers from, we're getting 2 numbers from the statistic, it's no longer on the Z table, it's going to be on the T table because this number came from the statistic and also that number is coming from our sample. And so we have a little bit more error. So we have a normal curve. We have kind of this deal going on. You got more in the middle, remember 68%, 95%, 99.7%. And that's our normal curve. So it would have a mean of 0 and a standard deviation of 1. But our t-distribution, if we lined it up on the same number line and looked at it, it's going to have more areas out on the wings and be flatter, because it really allows for more error because of using two numbers from a sample. Okay, so this is our t-distribution. Okay, and the reason we're doing that is because we're trying to estimate two parameters. Using statistics, so there's more variation. Okay, so this is only going to happen on the means. When we're doing proportions, we'll still use what we've always been doing with this z-star. So remember when we were naming our procedures, we always said with a z-interval or z-test. Now we're going to have a t-interval and a t-test because we have to use this other distribution. All right, let's go and take a look at the back. Right, the next table back, you had your table A for your z-scores. The next table past it is going to be table B, and that is going to help us with this is our t-distribution. Okay, so there's a couple things that's a little bit different. We have something here called df, and then these numbers that run down from it all the way to infinity. Okay, so what df stands for is a degree of freedom. Okay, and your degrees of freedom is your sample size minus 1. So this is part of that conservativeness in numbers that comes in from statistics, that they worry a little bit, you know, they don't want to overestimate, they'd rather under just a little bit. So in this case, so if our degrees of freedom equals n minus 1, we had a sample size of 30, and we're going to subtract 1, so we have 29 degrees of freedom. And really, it kind of, if you think about, if I had 5 people that I was going to sit in seats, and I have 5 chairs, the first person has 5 chairs to choose from, the second person has 4 chairs to choose from, and on, but the very last person has no freedom to sit where they want. They only have one choice. So that's kind of the idea behind this, the degrees of freedom. Now, we're going to go take a look at table B. And we're going to go down the side, and we're going to find where the degrees of freedom equal 29. Okay. All right, let's get a little bit closer here. So I'm going to go down and find my degrees of freedom of 29 right here. And we were going to construct a 95% confidence interval. So if you look across the bottom, it says confidence level. So you can find the interval that we want, which is 95%. And we're just going to come, and where they cross each other, that's our critical value. So in this case, 2.045. Okay, so with our 95% confidence, we're going to end up with a t-star of 2.045. Okay, so on our proportions, I had you memorize some of these, the critical values. You really aren't going to be able to memorize critical values for the t-distribution because it depends on your sample size each time. It's just a little bit different each time. All right, so we're going to calculate the margin of error using our critical value and our standard error. So remember, your margin of error equals t-star, and it's going to be times your standard error. Okay, so our margin of error is 2.045, which is our critical value, and then we had a standard error on the front of the paper of 0.0149. We multiply those together, and we're going to get a margin of error of 0.0305. All right, so now remember, when we had our point estimate and we wanted to create our confidence interval, you take your point estimate plus and minus your margin of error. Okay, so we had a point estimate of 11.1921, and to that number we're going to add and subtract our margin of error to create our interval. So when I subtracted, you should always put these in order, smallest to biggest. When I subtracted, I got 11.1616, and when I added the margin of error, I got 11.2226. So that's our confidence interval for the means. Remember, these are not proportions. So remember back to our proportions and interpreting the confidence interval. Pause the video and try and interpret this and see how you do. All right, so we are 95% confident the interval from 11.1616 to 11.2226, make sure you include the units here, grams, captures the true mean weight of Oreos. Okay? Hopefully you remembered how we did that for proportions. So now our specific formula. So we have kind of this generic formula going up here, but specifically, where is the point estimate coming from? Well, when we're talking about means, it comes from the sample mean. And to get your margin of error, you had your t star, and your t star is going to be multiplied to your sample standard deviation divided by the square root of the sample size. Okay, so this will be, it's very similar to finding the proportions. We just are coming from kind of a slightly different point in getting our critical value. Now, according to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 11.3 grams? Explain. Well, look at our confidence interval. It starts and ends less than 11.3 grams. So yeah, we have convincing evidence. 11.3 grams is not contained in our interval. And that's not done explaining it. It just says it's not in the interval. All plausible values were less than 11.3 grams. That's really the explanation. So 11.3 is not in our interval because all the plausible values in the interval are less than 11.3 grams. Okay, if 11.3 grams was in our interval, then we don't have convincing evidence. Okay, all right, let's summarize this down and see how we're doing. All right, there are two things that we want to kind of focus in on here in our important ideas. One has to do with critical values. So our critical value is our t star. And we're going to use it to estimate means. Okay. When you have a z star, not a z star, a t star, you have a degrees of freedom. And to find your degrees of freedom, you take your sample size minus 1. Once you do that, you're going to go to Table B, and you're going to use the degrees of freedom and the confidence level to find T star. Okay, now let's look at Table B again real quick. So I look at these degrees of freedom. I have individual numbers up to 30, and then I go from 30 to 40, 40 to 50, 50 to 60, 60 to 80, and I start jumping 100 to 1,000, and then 1,000 to infinity. Okay, so obviously all of the numbers, all the possible sample sizes are not in this table. So when you're using your table and you find your degrees of freedom, very important to remember, if it's not one of the numbers listed there, you will always round down. If your degrees of freedom is not in the table. That's another one of those conservative things that it's better to underestimate than to overestimate when using your statistics. So if I had a sample size of 35, my degrees of freedom would be 34. 34 is not on the list, so I would round down and use the degrees of freedom of 30. Okay? All right. Then our conditions. They're pretty much what we've been talking about. We have our random. And random is so we can generalize to the population, a random sample. So you could really have a random sample or a random assign. Okay. If you have a random assign, you don't need to worry about the 10% condition. That's when you're taking a sample. 10% is your sample size has to be less than 1/10 of the population when sampling without replacement. Now our third one, we used normal or large sample here. So there's really 3 ways to check this condition. They range from very, very easy to, and hard is not the right word, but just it takes a little bit more time. How about that? So our first way is the population distribution is approximately normal. This is the easiest way. If it says it in the problem that the population is approximately normal, you're set. You say we're okay here. Okay. The other way is they don't talk about the population's distribution, but you have a large sample size, meaning your sample size is greater than or equal to 30, so you can have the central limit theorem kick in. And you can abbreviate that CLT. Okay. The third way, this is the one, if your sample size is not big and they don't talk about the population distribution, if you have the sample data, this is your last resort, okay? You need to examine a graph of the data, so you would need to put it into your calculator and take a look at the graphing of it. And you want to see so that the graph shows no strong skew or outliers. And you would have to draw a sketch of the graph as part of this. Because it'd be like having a naked number otherwise. You can't make a statement. You have to have some evidence of it. So if you're forced to do this last thing, you would have to draw a quick sketch of the graph that you investigated. All right, go ahead and try the check your understanding. It has you trying a couple different things on the table B. And then number 2, check your 3 conditions and see if you meet to be able to go forward with your confidence interval. Check the key to see how you did. Let me know if you have any questions, and I'll see you in class.